Okay, so the progressive traveling, the progressive or this thing wave, I said that it's a disturbance or a pull that conveys energy from one point to the other without the transport of the matter itself. I hope you get that one. I've already explained it.
Yes, sir.
And I'm saying that depending on the direction of the particle vibration, the direction of the vibration, with respect to the direction of the travel of the wave, we can group that progressive wave into two, or we can distinguish them into two types. The first one we are saying is the transverse wave, and the other one we are seeing is a longitudinal wave. One can be transverse wave, one can be longitudinal wave under the progressive wave based on their direction of travel. Mm. With respect to that of the travel of the wave, or the direction of the particle vibration, with respect to the travel of the wave, we can see that it can either be transverse or longitudinal. Do you get it to? Do you get it to that point?
Yes, sir.
Good.
Yes, sir.
Now, when we talk of a transverse waves, when we talk about a transverse wave or transverse waves, we are saying that a wave is said to be a transverse wave if the direction of the travel, I listen, if the direction of the travel of the wave is perpendicular to the direction of vibration or displacement of particles of the medium. Let me explain it again. A wave is said to be a transverse wave if the direction of the travel of the wave, so the direction at which the wave travel, is perpendicular to the direction of the vibration. Are you getting it? Direction of the vibration of the medium. So here, if we are talking about water, then we are saying that the medium, the rate at which the water will vibrate when you drop a stone in it, is perpendicular to the direction of the wave. Then we are saying that it is a transverse wave. However, if they move in the same, what do you call it? It's not perpendicular, but they move along, or it travels in the same direction as that of the direction of the wave. Then we are saying that it is longitudinal. And so we are saying that a wave is said to be transverse wave if the direction of the travel of the wave is perpendicular to the direction of the vibration. That is the displacement of the medium, or the particles. So example is a plugged string, a plugged string and water waves, a plugged string and water wave. You realize that when you dip a stone into water, the stone, the vibration of the stone acts perpendicular to how the waves travel. Have you seen it? And so it will look like this. Let me just give you this. So you realize that when, if this is your water, if this is your water, you realize that when you drop a stone, you see that ripple effect on the surface of the water, and that's the travel of the wave. However, the vibration is done perpendicular. That means that the vibration of what they call the water is done perpendicular because the stone is placed perpendicular. You get it? They cut the water, and so you realize that the direction of the vibration is different from the direction of the wave. Are you getting it? It is perpendicular to that of the wave. Do you get it?
Yes, sir.
Exactly. So it's the same way the plug string, like the guitar and so on and so on. It's the same way they also act. So uh, these are examples of the transverse waves. And so when we are plotting it, we can plot a graph of maybe, uh, these are normally wave graphs. You realize that you have something like this. So there's it. Now, this part, this compartment, we call it crest. We call it crest. Under a transverse wave, we call it crest. ST. And here, the one in the negatives, we call it trough. Call it then it shows the direction of, or the travel of, what do you call it, a transverse wave, and there's a plot against, there's a displacement. Here's displacement, you can name it y, and time, a plot of displacement against time. And the crest represents the maximum displacement, the maximum displacement of, what do you call it, the maximum displacement of the wave, and the trough represents the minimum displacement of the wave. Do you get it? That's why when you look at a typical Cartesian plane, you realize that this one is in the positives, this one is in the negatives. Mm. negative, and this is strictly positive. You can see in terms of displacement, this one is in the negatives. This is them. Please, are you getting it? And so this one is
Yes, sir.
this one is a displacement, and this one will be the time it takes for the maximum displacement, or the time it takes, or the time direction of the travel of the wave, or the time it takes for what they call the displacement. Now let's also talk about longitudinal. With the longitudinal wave, as I said, is a vice versa, or is the opposite of the transverse wave. Unlike the transverse wave, this one, it occurs when the vibration is in the same direction as the travel of the direction of the travel of the wave. And so you realize that this one is in perpendicular to this one, but in the other way around, it's either they are all moving this way or they are all moving this way. Are you getting it? So one can be the direction of the wave, and one can be the direction of what do you call it, the vibration. But however, they are traveling in the same direction, or they are moving along or in the same direction. That one we call it a longitudinal waves. Please, have I made myself clear?
Yes, sir.
And in that wave, normally what they do is the vibrating particles normally behave like a spiral spring. When I say like a spiral spring, you see how they move, it behaves like this. It behaves something like this. So it gets to sometimes it get compressed, and it gets sometimes like it gets what do you call it? There's a gap between them. Some get compressed, and sometimes there's a gap between them. Now, the one with the gap, we call that one rarefaction. 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 It's other than rarefaction. Rarefaction. Can you please see the writing? Then the one which is this, we call it the compressed one. We call it compression. So we call this one compression. The side which is compressed, we call it compression, and it is, is synonymous, correct? Maybe synonymous or analogous to that of what do you call it? That of the crest and the trough. Are you getting it? That of the crest and the trough. So in this case, the compression.
Sir,
You said, when I say is analogous, I'm just trying to say that.
Please, the English.
Sorry, if I say that is analogous, I just mean that it's the same as the crest and the trough in this instance. And so here the compression is the crest, and here the trough is the rarefaction. I getting it? But normally, when we are talking about transverse waves, we use crest and trough, and we are talking about longitudinal, we use compression and rarefaction. But they are basically analogous, like they are basically the same. Let me put it that way. There are some instances you can also represent this by you can do it this way. So where they are compressed, you can just do it this way. Then you leave a space, then maybe you can come and continue. So within a space, we call this one is the rarefaction, and we can call the compression, what do you call it? This one compression. You can also represent it this way. So this is CSRC, and so on and so forth. Are you there?
Yes, sir.
Good. Now we can also talk about the difference between like the longitudinal and the transverse waves. And just looking at the explanations, I said that with the longitudinal waves, the particles of the medium or the vibration of the medium are normally parallel, or they move along with that of the wave motion. However, with the transverse, the particles of the medium or the vibration of the medium is perpendicular to that of what do you call it, the wave motion. And normally the longitudinal are made up of compressions and rarefactions. However, that of the transverse is made up or are made up of crests and troughs. Now the distance between the two successive compressions the difference between the two successive compressions and two successive compression is what we call the wavelength. So the distance between two successive compressions is called wavelength. However, when it comes to the transverse, the difference between two crests or troughs is also called wavelength. And so when you look at the longitudinal wave, there's the difference between two successive compressions or refractions are called wavelength. And the transverse waves, that the difference between two crests or two troughs are called what do you call it? Wavelength. So for instance, I do something like this. Let me use that of the transverse waves. I can continue. So from here to here is one wavelength. That's a complete distance. From here to here. From here to here is one wavelength. From here to here is half of a wavelength. From here to here is 1/4 of a wavelength. We explained when a class advanced, so don't worry. But from here is a crest. So from here to here is a wavelength. From here to here is a wavelength. From here to here is a wavelength, or distance, in other words.
Yes, sir.
Good. Now there's something called seismic waves. Seismic waves, and basically these are the waves of force that travel through the earth or other elastic bodies. For example, as a result of earthquake, explosion, and other processes that impact the forces to the body. And so that waves, as a result of earthquakes and so on and so forth, we call them seismic waves. And normally they are found or located in the earth. That has to, when you open the earth, you have the earth crust, the mantle, the core, and so on and so forth. And so that waves are distant found there. And normally we have the seismologists, they study about all those things. And the waves in the earth and so on and so forth. As a result of, it can be as a result of the disturbances on the earth. You get it, and so on and so on. And as a result, if it becomes too much, then we have the earthquake and so on and so forth. When there's a lot of pressure on the earth crust and the rest. Now the waves that occurs, the systemic we are also, and they are in the ground. They are continuous. They are always working in the ground. The ocean waves and the wind, they are all one another form of seismic distance. This one I won't delve much deeper. You can just go and read about it. So, and we use the scientists or the geophysicists. The geophysicists normally they use what we call seismograph to record the output of the seismometer. The seismometer is what do you call it? Something to calculate the waves, the movement of the waves, and so on and so forth, the speed of the wave and the rest. And they are able to tell. That is how come the geophysicists can be able to tell that okay, within the next hour or 5 or something, there can be an earthquake here and so on and so. They're able to predict with a distance. With this one, and we have two types of the seismic waves. We have the body waves and the surface waves. I won't talk much about it. Go and read about it. This is our reading. Are you true? Ruben, there's a spelling of the seismic.
Yes, sir.
Seismic. So that now let's also consider some terms used in describing a wave. 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 So terms that we are going to use under wave. Some terms used in describing a wave. I've already mentioned some of them, but let's just delve much deeper. Now, the first term we are going to consider is what we call amplitude, and it is denoted by small a. Amplitude. It is denoted by small a. You know how to spell amplitude. Amplitude. Now, when we talk about amplitude, we are saying that is the maximum displacement of particles from its or from their mean position. The maximum displacement of a particle. So if you have a particle at point A or at point O, the maximum displacement of it. So here, when you trace it to this point, the maximum displacement, how high it is displaced. The full distance is displacement, but the maximum displacement of it is what's called amplitude. The height is reached. Are you getting it? And so the maximum displacement of a particle from its mean position is what we call the amplitude, and it is measured in meter or in meters as a distance, so it's measured in meters. The maximum displacement of a particle from its mean position. So this is the mean position. Now the maximum displacement is what we call it can be like this. Is what we call the amplitude. Have I made myself clear?
Yes, sir.
Now, after amplitude, we are going to talk about period or time. Period. We are going to talk about period. Period. Now, when we talk about period, we simply mean that it's the time required for a particle to perform one complete cycle or to complete an oscillation. And so the time it takes a particle to complete an oscillation or to complete to make one complete cycle. So the time it takes a particle to make one complete cycle. You know, when you add this one to this one, becomes one complete cycle. So that the time it takes this to move from here to here is a complete cycle, and it takes this one to move from that's a complete cycle. So the time it takes a particle to make one complete cycle or one complete oscillation is what we term as the period, and it is denoted by capital T. And the SI unit is seconds. You know. Are you true?
Sir, yes.
Good. Now we're also going to talk about frequency. When we talk of frequency, we are just trying to see that the number of complete cycles or circles which the wave completes in 1 second is called the frequency. So the number of complete cycles the wave will complete in 1 second is what we call the frequency. So if how many distance, so depend on the energy with which the thing is vibrating, how many cycles is it will it be able to complete in just a second? That is what we call frequency. Are you getting it? And its SI unit is Hertz. Hertz. HZ, capital H, small z.
Sir.
Good. So when the displacement side is y, the distance here is x. You can see the distance along the horizontal axis is x. That's the distance between this and this, this and this, this and this. Now the distance between this and this, or the distance on the x-axis, is what we call, or the distance between two successive crests or two successive troughs is what we call or two successive compressions and refractions is what we call wavelength. So the distance between this and this, from here to here, is a wavelength. From here to here is a wavelength. From here to here is a wavelength. Are we true? You can also see that the distance covered by
Yes,
a wave
sir.
after one complete cycle. So the distance covered by a wave after one complete cycle can also be called wavelength. And because it is distance, it is made in meters as well. And so that is it. There's how it is written. It is denoted like this, as a wave. And it's made in meters. So amplitude is made in meters.
What is
Is there? There's a sign of a wavelength. There's how a wavelength is
no?
drawn.
I said what? How is one cycle?
How is one cycle? So you don't worry, we will talk about. So one cycle will be one complete wavelength. So from here to here is one cycle. From here, when it completes one side, is one cycle. When it moves another from here to other side, is also another cycle. Do you get it?
Yes, sir.
Good. So you can see from here to here, I just do so from here to here is one cycle. So from here is equivalent to one wavelength. One wavelength. And so you realize that from only here to here will be to what do you call it, half of the wavelength. Likewise, from here to here to be half of the wavelength. I hope you know that. That's mathematics. So from here The whole of year to years have wavelength. So that is it. Then half of this will be 1/4. 1/4 of the wavelength. 1/4 of the wavelength. Are you true?
Yes, sir.
Good. Now, the distance which the wave travels in 1 second is called wave velocity or velocity speed. So the distance the wave travel in 1 second is what is called the wave velocity or the wave speed. Yes, so the distance, so if the wave is able to travel from here to here within a second, the distance all over the time will become the velocity of the wave. Are you getting it? And it is denoted by velocity. You know, velocity is denoted by v, and it is made in meter per second. You got me?
Yes.
Good. Now let's look out for some relationship between all these terms, the velocity, the frequency, and so on and so forth. This you already know, but let's just take our time and go through. So you realize that frequency is equal to 1/t. So the terminologies I give, frequency is equal to 1/t. You know, this is the one distance. But you also know that velocity is equal to distance all over time taken. Please, I hope you agree with me.
Yes.
Yes, but here the distance here is the wavelength. Do you agree? So velocity will be equal to wavelength all over time taken. The time taken here is the period, so all over t. But t is also equal to, looking at this, we can get t in place of f. So t is also equal to 1 all over f. Change of subject. So we can also say that v is equal to this all over. Let me just. I want you to get it well. So that will be 1. You know this, we can simply write this one as this t times. You know we can write it this way. So 1 all over t2 we know is f. So we can say that v is equal to f times frequency. So velocity can also be frequency times wavelength. They also agree. And there's a wave equation. You need it in most of your calculations. There's a wave equation. Velocity, the speed of the wave, or the wave speed is equal to the frequency of the wave times the wavelength. Are you there?
Yes.
Good. Now let's do some provings. Let's do some proof under the wave equation, progressive wave equation. I can decide to name here the origin. I can decide to name this point maybe A. Or P. So we have this. Now, when a particle is displaced, when a particle moves from left to right, you know, looking at the direction, you realize that it's moving from left to right. The particle is being displaced from left to right. Now, when a particle moves from left to right, you bear with me that the particle at the origin, which is O, will be displaced before a particle at P. So you realize that the particle here will be displaced before this particle at P. This one will also be displaced before this particle at A. Do you agree with me in that way?
Yes, sir.
In this case, a particle at O what do you call it? The particle at O, or the origin, will be leading this particle at P, whilst this particle at P also be leading this particle at A. Do you also agree?
Yes, sir.
Good. Now, mathematically or scientifically or in physics, you can say that it's either the particle at O is leading the particle at P, or you can say that P is lagging on the particle of O. It means that O is leading P. So in other words, you can say P is lagging. You get it? And it's as a result of the angle, the phase lag. It's as a result of the phase lag, which is the angle between here. The result of the angle between here. So let's consider O and P. So as a result of the phase lag, this we call it phase lag. And so this one is lagging. This one is lagging by this phase, this angle. It's lagging by this angle. Are you getting it? So we call it
Sir,
phase angle.
L-A-G-G. L-A-G. L.
I don't get it. You said
A-G-G-I-N-G. Sir,
the lag.
please, is the lagging spelled L-A-G-G-I-N-G?
Yeah, exactly. Or lag. Lag. L-A-G. So that is it. So that's P. That is P. So sorry, something is distracting. Sorry. So that is it. We are saying that P is lagging at this by this angle. So the angle here we call it phase lag. Phase lag on O. Phase lag on O. Now we are going to talk about this. From here to here is a distance. So we can name from here to here is a distance on the x-axis. So we can see from O to this point, we can name it x. Now from here to here makes one complete oscillation. From here to here makes one complete oscillation. So we can name this one to our wavelength. Do you agree? So from this point is it makes one complete cycle. So that one to this one. So the displacement of the particle at O will be given by, so the displacement of this particle at O, if you've done circular motion, the displacement from this particle at O will be given by, the displacement is y. So the displacement will be equal to the maximum height it attains, which is the amplitude. And because it is a circular distance, now will be a sine omega t, where the omega t is the angular velocity. If you've done circular motion, you understand this. So a sine omega t. So we are going to get something like this. Yes, Ruben, talk to me.
Sir, please, we've not done circular motion.
Okay, sorry. Maybe we'll do it after this. So a sine omega t. Now the omega t and the circular motion, we call it angular velocity. And when we say angular velocity, if it was to be a linear velocity, you say that the rate of change of displacement with respect to time. But this one, because it moves in a circular path, we call it angular. So the rate of change of angular displacement. You get it? If it was to be the normal linear velocity, you say that velocity is the change in the rate of change of displacement with time. Here, that's why we call it angular velocity, because it's moving. This one is not linear; it is moving in a circular motion. So that one we call it angular velocity. So its displacement we call it angular displacement, because the displacement is moving in curves. Are you getting it? So that is it. So there's the displacement. The displacement will be, that means the displacement will be this a sine omega t, and you know what the time is. Now because the displacement p lags on O, because this p lags on O, there will be a minus, because we are talking about the full thing. So there's the angle here. So the angle, this will be like this, a sine A sine. I could have just written it, but I just want you to get it. This will be our last. What are we doing? A sine omega t minus this, where this is the phase angle on which this one is lagging on the origin. Hmm? Hmm?
Yes, sir.
Good. So this one we call it phase angle. We call it phase angle, and it is negative because it is lagging. Hmm? This one, the origin is leading it, so it is lagging. Hmm? So the negative means that the particle P, the particle at point P is lagging on the origin. That's what it means. So anytime you see it, you're saying it's lagging, it is leading it. Now, this lagging can be expressed as, this angle here can be expressed as, let me just write it simply. No need to talk too much about it. 2 pi x. 2 pi x all over this. So you realize that twice of, because this is a circular distance, if you have to talk about listen, so twice of this x will make this one. Abi, you know that twice of this x, the x is from here to here. Twice of this x will make this one. And so we are saying that because the circle and all those things, I don't want to go into this, but the phase angle is given by 2 pi x all over the wavelength. So that is it. Now we can factor this one here.
X and the wavelength cancel if
Is
they
it?
are the same. Won't
Yeah.
the 2x and the wavelength cancel if they are the same?
No, in this case, we are not considering it that way. In this case, we are not going. Now, yeah, because we are using a 2 pi because you realize there's 2 pi. You are using the 2 pi because you are talking about a certain circle and so on and so forth. That's how come we see the 2 pi, so on and so forth here. So in this case, this looks like, let me say, maybe a radius or something. Am I getting it? All over.
Yes. Yes,
So
sir.
2 pi. So we can say 2 pi r or something. So because when you stand here, you should be able to draw when you add this one or something. So let's just see it that way. I don't want to. So we have this. I'm hungry, pal. So we have this. So we can factor this one into this. So we are going to get the displacement is equal to A sine into bracket omega t minus 2 pi all over this. I hope you agreed to this point.
Yes, sir.
Good. So that is it. So we can say that our progressive wave can be given as y is equal to a sine omega omega t minus 2 pi x all over this. But you know that this one can also be, when we're doing our mathematics, listen, we know that v is equal to all over t. You saw this, eh? I give you this. V is equal to wavelength all over t. V is equal to wavelength all over t. So we can, however, so we can also say t is equal to, looking at this formula, we can say t is equal to this one all over v. And looking at this here, omega t is equal to 2 pi omega t omega is equal to 2 pi all over t. Omega is equal to 2 pi all over t. In angles, one complete distance is 2 pi. In angles, this we did this when we were doing the radians and the rest. So
Please
yes,
be
2 pi.
careful with the confusing.
Is it?
The T. You are using 2T. capital and then there's small t. So the one you've written is small t. So
So what has it done? The whole time.
so
The whole time. Just we are using a what do you call it? I don't even know how to explain this. But let's take it as the whole time. When we are solving questions, you understand better. Next time when we are solving questions, you understand better. So uh we can rewrite this. We can factor any of this into this and rewrite the equation again. So we can say uh because we've not done with circular motion, I don't know, but this can also be equal to, t is equal to this, so you can put this one here, so we can get omega is equal to 2 pi v 2 pi v all over this. Looking at this calculation, omega is angular velocity is equal to 2 pi all over t. The 2 pi here is a distance, I've told you, all over time. And here, but here, because we are talking about angular, so the angular distance all over time. Angular distance all over time. And but t is also equal to wavelength all over v. So we can just substitute and come and get omega is equal to 2 pi v all over distance. So anywhere we see omega, we can factor the whole of this here. So we can rewrite y is equal to, after proving this, then we are done for the day. So this will be sine into bracket 2 pi v all over omega minus, here is 2 pi x all over this. Can you see it? So we can relate them in terms of distance. So 2 pi v all over this minus 2 pi x all over this. X is a distance, v is velocity, and so you can however even do factorize 2 pi out. So you can get y is equal to a sine 2 pi into brackets v all over wavelength minus x all over wavelength. Have you seen it?
say, there was another t beside the omega.
Which oh, so there will be a small t here. I forgot to write. So there's small t here. Please write it. I beg. Write a small t. Add it. Can I clean the board? Can I clean some part of it?
But say the small t is it also equal to the wavelength all over the velocity?
So don't worry. I said when we are solving question, you get this thing. So this small t comes from the wave. What do you call it? This circle, because you've not done this thing, so you can get it. But it's also time. It's also time, and we can also use that in what do you call it? Your calculations, your normal calculations, like the wavelength all over this and this and this. But I just want you to understand something. When we are solving questions, you get it better. Are you true? Are you done writing this? I want to clean some parts so that we finish it up. Then we are done. I'm hungry. We can also rewrite this as we can also
So wait.
we can also write y is equal to a sine you know that, but v all over this all over this is also equal to f. This all over this, v all over this. This one, v all over this. F can also be equal to v all over this. V all over omega. So in place of that, we can factor f2 here. So we can also write this and write 2 pi ft, 2 pi ft, 2 pi ft minus 2 pi x all over wavelength. Have you seen it? And this is a progressive wave equation. We call this progressive wave equation. And you know that y Y is any particle from the origin, the displacement of any particle from the origin. V is the velocity above, you know, and x is the distance of the particle from the origin. X is the distance of the particle from the origin. So x is the distance of the particle from the origin. I've already said that. And A is the amplitude. That's the maximum displacement. F is the frequency of the vibrating particle. And so the time is what it takes for a complete distance. So that is it. So there's a wave equation. There's a wave equation. Now, when it is this one, we write this equation when the wave is moving from when the this one is when the wave is moving from what do you call it, left to right. So when it is negative, when the wave is moving from left to right. However, this negative change to positive when the wave is moving from right to left. That means when you're reversing the equation, when it's moving from this side to this side, we make it positive. When it is moving from left to right, it's negative. So you realize that the diagram I drew was from right to left. Sorry, it was from left to right. So that one, this one is negative. That's how come we're getting this to be negative. In that case, what it simply means is that you realize that I do something like this. Let me just explain it before I close. You realize that when this is moving from this point, we assume that at point P, this one is lagging on this. So as a result, here it's made negative. However, when it is moving from this side to this side, it becomes a vice versa. That's how come we are going to get when it's moving from right to left, it becomes positive, and when it is moving from left to right, it becomes negative. So in this case, here will be leading. In this case, when it is moving from right to left, this side will be leading this side. But when you move from right to left, left to right, this side will be leading this side. When you move from right to left, this side will be leading this one. And so when it's moving from this equation is when the wave or the particle is moving from right, sorry, from left to right. So this is from left to right. However, when it's moving from right to left, you make it positive. That is it. I'm very hungry. Let me go and eat. Next week we are going to solve questions on it, calculation questions on it. Or you yourself go and solve
Okay.
questions. Next week you meet, you also solve another questions on it. Then I have
Okay.
I have to teach you standing waves. So you do the standing waves too. Then we are done for the wave itself. Then we are left with only sound wave. Then we also do that one. By the end of the month, you finish everything on waves. Then I can, if you have time, I can start taking you through what we call it, the circular motion and the. I don't know if I have videos on circular motion. If I have, I'll check. If I have, I'll send them to you so that you start going through. Hmm? Circular motion,
Yes, yes,
circular
yes.
motion, and simple harmonic motion. I think I have. I should have videos on them. If I have, I'll send. If I think I have them, I'll check and I'll put it on YouTube or I'll send it to you so that you check. Yeah. Have a nice day. Evening.
Sir, please wait. Please upload the this thing on YouTube.
I hear. I will.
So I'm waiting.
I will.
Sir, thank you
You're
very,
welcome.
very much.
You're welcome. Bye.